So hello everyone, my name is Manish Kumar and I am a current PhD student at ISER Kolkata. So I'll be taking this live sessions for the course Dynamical System and Control. Okay. So let's begin today's session. So today I'll mainly talking about Picard's theorem. Okay. I'll state the theorem. I'll give an overview of what you have seen in the first week and then a few problems related to that. Okay. So this is how I think. Okay, so this is what you were introduced about this dynamical systems. Okay, so you already saw that what is a system. System is just a collection of some objects. Okay, and they are related to each other by something. Okay, so that is the abstract, just a vague definition of system. What we will be interested is the system which are described by some differential equation, more specifically the ordinary differential equation. Okay, so the dynamical system, as the name suggests, that it has a dynamic, so it is dynamic. That means it will change as the time passes. Okay, so it's not static, it's dynamic. Okay, so and you already you can understand what are the practical examples like motion of vehicles, satellites, this population growth, and you already saw some examples like, for example, this population growth model. You already saw all these examples, so I'll just introduce all those again. I'll just mention what the system is. And okay, so let's move further. So differential equation is just equation which involves the function and its derivatives, right? So the differential equation is just the relation between the given function and its derivative. Okay, so it's just a function of so let's say if y is a function, so differential equation can be defined as f of y. Okay, so depending on how many dependent and independent variables are, so either it will be, suppose y is just a function of t, then the function of the sort f y prime till nth derivative equal to 0. So this is what the general form of differential equation is, ordinary differential equation. Now the moment you introduce some other variable, another independent variable, so for example x, then this can be written more generally like which constitute both the time derivative as well as space derivatives. Okay, so that's the general formula or the representation of differential equation. Okay, so the differential equation is called ordinary if there is just one independent variable. Okay, and if there are more than one independent variable, then we say it's the differential equation is partial differential equation. Okay, so I've given one example of each. So in this case, when y is just a function of t, so this is the an example of ordinary differential equation where the derivative y prime is equal to y. So this is the equation which involves derivative and y. Okay, and this is the partial derivatives. Okay, so this del y by del t means that you are differentiating y partially with respect to t and partially with respect to x. So this is the transport equation, yt hyperbolic partial differential equation. So this equation is a partial differential equation just because this is a function of two or more variables and it involves derivative of both. Okay, in this particular example. So this is what a differential equation is. So let's see a few classifications based on linearity or non-linearity of the differential equation. Okay, so as I mentioned that this is the general form of ODE. Okay, so ODE is just ordinary differential equation, short form for that, where yn is just nth derivative of y. Okay, and we'll consider in particular of this type of differential equation. Okay, so so I think you already saw that suppose y prime y double prime plus y prime equal to 0. Like if you have a differential equation of this sort, so this is considered, this is f y prime y double prime. Okay, so suppose this is the operator, differential operator, and this is given to you. Now from here you can deduce that if you take y prime common, you will get y double prime plus y equal to 0. Okay, so from here there are two differential equation which is coming out. Okay, so we will not consider differential equation of this sort. So what we will consider in particular differential equation of this sort, what means that the highest order derivative, so here n is the highest order derivative of y which is involved in the equation. In this case, like for example the second okay, so what is order? So let me first define the order of differential equation. So the highest order of the derivative what is present in the equation is called the order of the equation. For example, this y prime plus y equal to 0. So in this case the highest order derivative is 2. I mean the second order derivative, right? So this, the order of this differential equation is 2. Okay, so when you can write the differential equation in this form, where the higher order derivative can be written as a function of its lower order derivatives and t. Okay, so t is the independent variable which is involved in this equation. Okay, so this is, we'll consider this type of equation only. Okay, and later on we'll see, we'll just talk about the first order derivative, I mean first order differential equation. Okay, so this type of differential equation will be taken into consideration, and so now we'll say when the differential equation, ordinary differential equation, is linear or not. Okay, so for that what we can do, so just consider the terms which involves y and its derivative. Okay, so if something is independent of this, I mean which is just a function of t, throw it on the right hand side. Okay, and consider all the terms involving y and its derivative on the left. Now define this as an operator, so dy given by this. Now if this dy satisfy the linearity property which is written here, that d of alpha 1 y1 plus alpha 2 y2 is equal to alpha 1 dy1 plus alpha 2 dy2. Okay, so this is for all alpha 1 alpha 2. In our case it will be r, this field k will be r, and this y1 y2 will belong to the vector space or the solution space of that differential equation. So if we have such linearity property, this property, then we say that the differential equation is linear, and if it is not linear, we say that the different ODE is non-linear. Okay, so this is the linear and non-linear ODE. Okay, so these are the few examples, like to whether the ODE is linear or not. So can you tell me about the first one? What do you feel? The first is linear or non-linear, the ODE?
Non-linear.
Sorry?
It is non-linear ODE.
Non-linear because of this term, right? It's quite clear that we have y prime thing, so it cannot be linear. So you can check that this is non-linear ODE. Okay. What about the second one?
Linear.
This is linear. So basically linear means linear in y, not, so we will not take in t into the consideration. So here this y prime y, these are linear, so that's why this, so you can all actually check. So here we can define this dy as y prime plus t square y, and then you can check this property. Okay, it's quite trivial to check. Okay, so this is a linear ODE. Again similarly the third one is third is also linear, right?
Yes.
Again the same reason. So you don't have to worry about these, which is function or which involves t. Okay, so you don't have to worry about that. So this is also a linear differential equation. Okay, linear ODEs. Okay. I hope this is clear to everyone. Okay, so you have seen these examples, right? So which is the physical systems which are modeled by ODs. Okay, so you saw this population growth model, right? So y prime is equal to ay minus by square. So this b so this is something which involves the interaction between the population. So if b is 0, this is a simplified population model where you do not consider the interactions between the two two people in that population. Okay, So the general model is this one, where A and B are called the coefficients, now vital coefficient of the population. Okay, and that's it. So this is a so if B is 0, you know the solution is given by yt equal to EAT and then this initial data y0. So this says that this is a exponential growth, which is not true in practice, right? So this A is basically the the growth rate of the population. Okay, this A. Okay, so this is the one of the example that you saw. Another example is this motion of pendulum that you already must have seen in physics course and in this course as well. Okay, so this is a second order differential equation, right? Okay, so from now onwards, what we'll see that. Okay, so let me tell you that suppose this initial value problem is, okay, I think I should have mentioned. So suppose this type of differential equation, okay, so this dy by dt is f of t comma y. Okay, and you have some initial data that y at time equal to 0 or time equal to t naught is y naught. Okay, now just a second. Now we'll study the solution of this kind of initial value problem, that when the solution exists, if it exists, whether it will be unique or not. Such kind of question will be addressed. So we'll be just considering the first order derivative, not the higher one. Okay. Okay, so notice this one. This is a second order ODE. Okay, but this can be converted. Okay, so here you can assume that y is not just in Rn. So yt you can consider that it is in Rn. That means y is a tuple. Okay, so y1t, ynt you can consider in this way. Okay, but we'll be, I mean, for in this session we'll be mainly talking about when yt is in R, but this type of system can be considered as a system. Okay, so in that way this second order ODE can be converted as a system of first order ODE. Okay? So do you know how to convert that?
Take y as y and y prime as the tuplet and then
Exactly. So I think, yeah. So you can take, so suppose you can assume that u is like y prime. Okay, then you can write this equation. Okay, so let's say y or z, let me write z. So you can take z as y prime, then z prime can be given as y double prime, which from equation gives you minus g by l sine of y minus k by m y prime, which is z, right? So you can write this as a tuple. You can write y z prime is equal to, so y prime is z, right? So this will be z and z prime is this whole thing minus g by l sine y minus k by m z, right? So you can write this second order differential equation as a system of first order differential equation. Okay, so so that's why we'll be mainly talking about the existence and uniqueness of solution for this kind of the first order ODE. Okay, so we'll now go to the theory which tells you whether this kind of initial value problem has a solution or not. Okay, so now we'll go to this question. Okay, so these were a few examples that you saw. Okay, so now let us come to this first order ODEs. So you have this kind of initial value problem. Okay, so you have a differential equation and then you have this initial condition. Okay, so such type of problem is called initial value problem. And what do we mean by the solution of this initial value problem, right? So it's quite obvious that how would you define the solution of this initial value problem, right? So it's like the function y, okay, this function will be called a solution. Okay, so I think here it will be 2. Okay, so it's called solution of this IVP2, okay, on some given interval AB if it satisfies the following. Okay, what are those conditions? The first thing is that to make sense of this y prime, it should be differentiable. Okay, so yt should be differentiable on I, and it should satisfy this equation. So the differential equation should be satisfied by this y, okay, for each point t in the interval I. Okay, so this is the the requirement for this equation to make sense. The second condition is that the interval what we are considering, that should contain this point t naught. Okay, so t naught should be in I, and y at t naught should be equal to y naught. So this is the second condition. Okay, so this is the classical notion of classical definition for the solution. Okay. So now the question is that when can we say that, okay, for a given equation, differential equation IVP, when does the solution exist, and if it exists, will it be unique always? Okay, so this is the question of existence and uniqueness. So in general, like whenever we talk about some differential equation, we talk about whether the solution exists or not, and if it exists, whether it is unique or not. This is called well posedness question, whether the equation is well posed or not, right? So you have already seen that. So to address these type of question, so what we'll see two theorems. Okay, one is called Piano's theorem, and the other one is Picard's theorem. Okay, so so let's go to. Okay, so before going to that, let us consider this example. So you have some idea of solving differential equation. Okay, so before going to study that what kind of function, so what kind of condition we should put on this f, t naught and y naught, so that the solution exists. Okay, so we'll see those questions to be addressed. Before going to that, let us see this particular example, okay, with these initial data conditions. Okay, so these are three initial value problems that we'll be considering. So let us see what this equation is. Okay, so the equation is ty prime minus 3y plus 3 equal to 0, right? So here we are considering t to be greater than 0. So you already know how to solve this kind of equation. So let us rewrite this equation as y prime minus 3 by ty. Okay, so you can see from here that this y and t can be separated. So let me write in this fashion, t dy by dt. So you can use the method of separation of it. So you can separate this y variable and t variable. Okay, so we can do it in this way. So t dy by dt, I can write it as 3y minus 1, right? Now I can take y term here, so dy by y minus 1 is equal to 3 dt upon t. Okay, so now if we integrate, what we get is ln mod y minus 1 is equal to 3 ln mod t plus some constant c, right? Now if I can write this as ln mod t cube. Okay, so t is positive, so I am removing the mod t cube plus c. So here I can make ln mod y minus 1 upon t cube is equal to c. If I remove the mod, I'll get y minus 1 is equal to e raised to power c. So again I'll call this e raised to power c again as a constant c. Okay, or if you want you can denote it by c tilde or something like that. So from here what we get is y minus 1 mod is equal to c tilde t cube. Okay, and then just so you have this formulation, and from here you can get, so suppose you remove the mod. Okay, so suppose y minus 1 is positive, then in that case you will get y minus 1 c tilde t cube, and if you do, if it's minus, you will get minus y plus 1. Okay, but again if you, so from here you will get y equal to 1 plus c tilde t cube, and from here what you get is y equals 1 minus c tilde t cube. Okay, but since c tilde is arbitrary constant, so c tilde over here is okay, so in this case it is positive. Okay, so let us keep both of them. Otherwise, suppose if c tilde was just arbitrary, because of this exponential it is becoming positive, right? But if c tilde was any constant, then we could have just considered any one of them, right? Okay, so I think you can see from here as well. Where is it? This point. Okay, whatever, let it be. So let us consider this one equation, this one. So if the solution yt is equal to 1 plus c tilde t cube. Okay, now we had some initial conditions, right? So far we have just solved this ODE. This ODE we have just tried to solve. Okay, but we had some initial conditions that has to be put there. Okay. Okay. Okay, so if I consider this one, so let me just see if both will work or just one will work. Here we had one information that t is greater than 0. Okay, so okay, so from here you can say this is greater than 0. From here you can probably say that y minus 1 is greater than 0. So this is corresponding to y minus 1 greater than. Okay, so you can delete this case. Okay. So from we know that t is greater than 0. Okay, so you can just, from here you can know that y minus 1 will be greater than 0 roughly, and so you just need to consider this case. Okay, so this will give you y equal to 1 plus c tilde t cube. Okay. So you have this as a solution of this differential equation. Now the moment when you use these kind of conditions, so we'll see whether this gives the value of c tilde. So far c tilde is unknown that we want to determine, and this will vary depending on the initial condition we have. Okay, so the initial condition what we have is y0 equal to 0, y1 equal to 1, and y0 equal to 1. Okay, so these are the initial conditions that we want to check. So let us begin with the first case. So here the first initial condition was that y0 0 is 0. So if you substitute t equal to 0 here, okay, how should I write? Okay, so if you put t equal to 0 here, you are getting 1, which is not equal to 0, right? So this, the initial condition. Okay, so the IVP, the initial value problem corresponding to the initial condition, corresponding to the initial condition 1a, admits no solution. Okay, so this, the first initial condition, if you take that into the consideration, then it will give no solution. Okay, let us see the second one. So the second condition is y at 1 should be 1, right? This condition. So let us put t equal to 1. So y1 equal to 1 plus c tilde, right? And you are asking that y1 should be 1. So this is equal to 1 implies c tilde should be 0, right? So in this case the solution yt, this can be rewritten as yt equal to 1. So this is giving a constant solution, right? So in this case we have a unique solution. So the IVP corresponding to initial condition B admits unique solution. Correct? Now let us see the third case. So the third initial condition is y0 is 1. Okay. So y0, if I put t equal to 0 uh, in this function, so y0 will give me 1. Okay, and which is matching with this condition. So there is no choice of c. I mean any c tilde would work. So in this case the solution is yt is equal to 1 plus c tilde t cube, where c tilde is any positive real number, right? Right, so here we are getting infinite solution. So the IVP with initial condition C admits a unique solution. So what is happening here is, so you see this differential equation remains same, right, all the time. So this differential,
Excuse me.
yeah,
Just a question. This it doesn't admit unique solution, right? There are many solutions.
oh sorry, admits infinite solution. Yeah, thanks for the correction.
And also one more question.
Yeah.
Like while trying to find the solution, you in one of the earlier steps we wrote dy by y minus 1 is equal to 3 dt by t.
Exactly.
But y is not here. We have to assume that y is not equal to 1, right? But the
Okay,
initial
yeah.
condition.
You are right. Correct. Because that would give t equal to 0. I mean, that is not possible. Okay, I got your point, what you're saying. Yeah. So here we are assuming y is not equal to 1. But then in the second initial condition, we are putting the condition that y1 is 1. Right? To solve that, okay, so see, understood. So you don't, so this condition can be dealt separately. So here you may assume, so here we are assuming y is not equal to 1. Now for this one, so this case, what you can do is, so here from here we can note, so if I put y equal to 1 here, so what I get is this differential equation is satisfied, right? So instead of going this way, I can just say from here, I mean looking at the equation, I can say, so for this case I can say yt equal to 1 for all t greater than 0 is the solution of this IV initial value problem. Okay, so I cannot guarantee the uniqueness. Okay, so far I'll just say that it is a solution. Okay, so let me write this case separately. Okay, so it cannot be solved. I mean, when y is 1, we cannot do this kind of analysis. Okay, right? So in this case, I'll just say that yt equal to 1 for all t greater than 0 is a solution of the IVP, right? Okay, I hope everyone got his point, what he was trying to say. That this I cannot, I'll have to assume that y is not equal to 1 to make all these calculations sensible. Okay, so what I was saying earlier, that it has a unique solution, now I cannot guarantee. Or maybe like by some other method we can solve. Okay, so this y prime equal to 3 by, so let me see in this way. So from here it's y prime minus 3 by ty plus 3 by t. I can do this step. Now I think you can use, so this is a linear differential equation, right? So this is a linear differential equation. Now you can use the integrating factor, and then you multiply this differential equation with that integrating factor. Then probably from that method I hope that one can get the solution. Okay, so you can check this method. So multiply by integrating factor and try to solve this. So I hope that in that method I don't think that this condition will be required probably. Okay.
Okay.
Is there any
Thank you.
other comment? Is this clear to everyone? Okay. Okay then. Thanks again for pointing this out. Okay, so let's. Okay, so in this problem, what we saw that the differential equation remains same in all the situation. What we are changing is the initial condition, right? So the problem IVP is changing in all the three cases, and also the solution what we are getting is also different in all these cases, right? So we'll see that what condition. So now, as I mentioned here, that you have to put some condition on f, okay, that will guarantee the existence of solution of the differential equation. But to solve this initial value problem, you have to put some condition, or I mean corresponding to this initial data. So you have to consider this t naught, y naught when you are trying to understand the solution of this IVP. Okay. Okay, so let us, okay, so this is another definition that we have for the solution of this IVP. Okay, so you already saw what the solution means. Solution basically means that y will be called a solution if it satisfies this differential equation and this initial condition. So y solution on I, so this I should contain this t naught, should contain this point t naught, and y at t naught should be equal to y naught. Okay. So this is what we earlier mentioned, that what the solution is. We saw this. Now we'll give another equivalent definition of this solution, and this definition was useful in proving the Picard's theorem, right? Okay, so suppose the function f is a continuous function, that the function what you are considering on right is continuous in both the variable t and y. Okay, and suppose t naught y naught is any arbitrary point in the domain. So this is the domain of the function d. And suppose t naught y naught is a point lying in this d. Okay, then this IVP, then consider this IVP. Okay, so these are the two assumptions that we have made, that f to be continuous and this t naught y naught point should be in the domain of f. Okay, now the proposition is, so earlier what we have mentioned, that for y to be a solution, you noted that y should be differentiable. The first thing is y should be differentiable. Okay, and then it should satisfy this kind of identity, this equation, and it should satisfy this initial condition. But now I am saying a continuous function y will be called a solution if it satisfies this kind of identity. So here I am not mentioning that y should be differentiable, but it is a outcome. I mean, it is an implication of this definition itself. Why? So when I say this y is continuous and this f is also given to be a continuous function, I mean we have assumed that. Okay, so look at this function. So this is just a function of s. Okay, so define this as a g of s. So now you know that this function f is continuous in both the variables and this y is also continuous. So you can prove that this g, the function g, is also continuous. Okay, so this integrand is also a continuous function of s. Now you can use the fundamental theorem of calculus to say that this y function is differentiable, and that if you differentiate it, what you get is y prime of t is nothing but f of t yt, right? So this is due to the fundamental theorem of calculus. Okay, so you got, from here you can understand that differentiability is coming just by assuming that y is continuous, f is continuous, and from this integral equation. Okay. So this is the proof actually. So this is the one-sided proof. Okay, so this is true other way around also, that if y is some function which satisfies this kind of if y is a solution, then it will satisfy this, and if y is a continuous function satisfying this, then y is a solution. Okay, and the proof is quite easy. So this is what the first proof, that if you assume that y is a continuous function which satisfies this kind of identity, then obviously this y is differentiable and y prime is this. Okay, and also if you put t equal to t naught, okay, then this will turn out to be y naught. Okay, and to prove the other way around, that if if y is a solution, then this kind of identity, you just integrate the equation. So if you integrate this from time interval t naught to t, you will get this kind of identity. Okay, so the proof is quite easy. It's not that difficult to understand. Okay, I hope this is clear. Should I repeat or should I proceed? So this will not be used in the further session, but this is something that you have already seen in while proving the Picard's theorem. So to prove that y is a solution, you use some kind of iteration, and that iteration is defined using this kind of integral formulation of the solution. Okay. Okay, so this is the theorem what we have. So this Peano's theorem, so what it says, so these assumptions are always there, that this t naught y naught, I don't know whether I've written it here or not. Okay, so this is not precisely written, so you can understand the same line. So f is a function from D, which is a subset of R2 to R. Okay, so as I mentioned earlier, that this f can be considered D subset of R cross Rn. Okay, so when you are considering a system of first order differential equation. Okay, so I mean the same theory will go for Rn as well. Okay. Okay, so this function f is from D to Rn, R2 to R. Okay, and this is a, so I'll assume this is the domain, and you will assume that the initial, okay, so the way we have defined is fine, so we don't need to assume that, because we have considered R to the place where we'll be talking about the properties of f, and this R is a neighborhood of t naught y naught. Okay, so how this R is, so suppose t naught y naught is some point in R2, so suppose this is t naught y naught. Now you take a neighborhood of this t naught, so this is t naught, this is t naught plus a, so let me represent here, this is, let's say, t axis, this is y axis, this is point t naught y naught, so this is t naught here, so this is t naught minus a, t naught plus a, and this is the y naught. So this is y naught plus a and y naught minus a. Okay, so you have to consider this domain. Okay, so this is the rectangle. Okay, so this is the rectangle R where we will be talking about the properties of f. Okay, so this will be
Hello, sir. Sorry for interruption, sir.
no, no, no.
So it will be the y naught minus b and y naught plus b. On the y-axis, it will be the y naught minus b. And
Oh,
y
sorry, I
naught
have
plus
written
b.
a. Okay, okay, right.
Yes, sir.
Yeah, thank you. Okay, so we have this domain, and what are our assumptions? That this function f should be continuous on this rectangle. Okay. Now when it is continuous, this is an implication that any continuous function on a bounded domain is bounded. So this is M is the bound. Okay, so this M exists. That is from this assumption as well. Now you define H to be minimum of this A and B by M. Okay. Then the IVP, so which is y prime equal to ft comma y, and y at t0 is y0. So this IVP will admit the solution. And what will be the interval of existence of the solution? It will be this neighborhood of t naught with the size 2h, where h is this quantity. Okay, so this t naught will be either equal to a or something less than that. So in this interval, the solution will exist. Is it okay? So what we are saying, that the function should be continuous in this rectangle, which is a neighborhood of t naught y naught, right? And the solution will exist if the function is continuous, and it will be given by some interval of t naught, which is at max it can be this t naught minus a to t naught plus a. Otherwise it can be less than that as well, depending on what this function f is. Okay, I'll give one example where we'll calculate what this h is. Okay, what maximum h we can attain. I'll give one example of that. Okay, so this is what this theorem says. So you see, you just have to assume that the function f is continuous. So just continuity assumption gives you the existence of solution. But we have seen in this example so here f of ty, any question? So in this example we have seen that f of t comma y is 3y by t minus 3 by t, right? So this function f was continuous in the open interval 0 comma infinity cross r. I mean, it is continuous with respect to r, with respect to y in everywhere, and with respect to t we'll just have to take I mean outside 0. Okay, but okay, I mean this function, but I don't think this satisfies the assumption. Okay, so this will not, so I was trying to see, so what I was trying to explain, that this function is continuous, okay, but this IVP, I mean this initial condition gives you infinite solution, but we cannot give this example to make you understand the uniqueness property, because here you see the function f was continuous on 0 infinity cross r, but this t naught comma y naught, what was t naught comma y naught? So for c I am saying this one. So it is 0 comma 1. Okay, so we'll have to take some neighborhood of 0 comma 1, okay, like this. But the function f is not continuous here, like in this domain, when t is less than or equal to 1. So we cannot use the hypothesis of Peano's theorem to guarantee the existence of solution. Okay, but let us try to, okay, I'll come to this later on maybe, or I can explain here itself. Okay, so consider this, now consider this B problem. Let me cut this off. Okay, so now consider the second initial condition, which was y1 equal to 1. Okay, so you have to consider a neighborhood of 1 comma 1, so something like this. Okay, so now you can take some delta where delta is greater than 0. Okay, in this rectangle you can see the function is continuous, right? So this is continuous on 0 infinity comma r cross r. So this is continuous in this rectangle, right? And so we have that this initial value problem admits a solution, this B. Okay, so this Peano's theorem will tell you when the solution exists. Okay, so this is a sufficient condition, it is not a necessary condition. So if this hypothesis does not hold, that will not mean that the solution will not exist. As in this case, the C part, we saw that the hypothesis is not being satisfied, right? In this case we saw that if you take any neighborhood of 0 comma 1 with this kind of neighborhood, the function is not continuous, but still it admits a solution. In fact, it admits infinitely many solutions, right? So the Peano's theorem is giving us sufficient condition that if we have certain hypothesis, like if this hypothesis is fulfilled by the function f, then it will admit, the IVP will admit a solution, otherwise it won't. Otherwise it not, we cannot conclude. So if it satisfies the hypothesis, we have unique existence of solution. If it does not satisfy the hypothesis, we cannot say anything. So this Peano's theorem is existential theorem, that when the solution exists, and so it gives some sufficient condition on the function f. Okay. Okay. Okay, so in particular, so here, so we have got, okay, the solution exists, we cannot say more than that, we cannot say whether it is unique or not. That will be given by Picard's theorem, we'll see in the next slide. But here only, along with the fact that the f is continuous, if you assume this condition that f is monotonically non-increasing in y, okay, so for each fixed t, so you just consider this as a function of y. So you fix some t, now you consider it as a function of y. If that is non-increasing, then this will have a unique solution. Okay, so here we just assume that f is continuous. Here I am adding one more hypothesis, that it is non-increasing in y. Okay, so can you prove it? Do you know the proof of this? No? Then I think I'll just give a sketch. Okay. Okay, so what I am saying, that suppose you have this equation y prime equal to f t comma y, so y at t0 is y0. So this is the initial value problem that you have. Okay, now assume that f is, so these hypotheses are always there. Okay, so with that assumption we have that okay, y has a solution under that hypothesis. So under the hypothesis of Piano's theorem. Okay, now I am putting an extra assumption that suppose f is non-increasing. Okay, then I'll prove that it will have a unique solution. Okay, so assume it has a two solution, so we'll prove it by a contradictory argument. So if possible, let y1 and y2 be two solutions of IVP. Okay, now consider this z as y1 minus y2. Then if you substitute in this equation, what you get is, so you can evaluate what z prime is. So z prime is y1 prime minus y2 prime, and that is equal to ft y1 minus ft y2. Okay, and this z at t naught will be 0, right? So this is another initial value problem that we have. This is star dash, let's star. Now we will focus on this IVP, right? Now my claim is, if I can prove that z is 0, then I am done. This will prove that y1 is equal to y2. Okay, and hence we are done. Okay, so what we'll do, so okay, so here let us mention that they are distinct solution, two distinct. Okay, so that means y1 and y2 are not same on all the points. So suppose this is the interval I where the solution exists. Okay, so in some interval of t naught. So from Picard's, okay, so from Piano's theorem, suppose y1 is a solution, that means it will have t naught minus h1 to t naught plus h1. Now for the second solution, it might have some h2 which is not h1. We don't know about that. So we'll take the minimum of that. So suppose h2 is this one, this length is h2, so t naught minus h2, so some t naught plus h2. So we'll take the minimum one. Okay, so we are considering on some interval, let's say t naught plus h, sorry, t naught minus h to t naught plus h. Okay, so this is the interval where we are considering the solution y1 and y2. Now suppose this, so at this point at t naught we know that both are same because of the initial condition. So we know y1 and y2 are same at this point. So suppose y1 goes like this and y2, because they are different, so maybe at some point it will be different, right? So suppose, so I mean the possibilities of y2 are, maybe it can go like this, it can go like this, it can be same till here and then it can change, right? There are many possibilities. So what we'll say, so what you can see that, suppose you get a point, so let t star greater than t naught. Okay, so I'm just considering this part, that will be sufficient for our proof. So suppose t star is greater than t naught, such that what it satisfies is, suppose y1 t star is greater than y2 t star. Since they are different, such t star exists, right? Because they cannot be equal, or the other way around, maybe not this but this, right? So I mean you can take any of the cases. So let me write it here, considering both of the cases. So either consider t star with this property and y1 t is greater than equal to y2 t, or consider this one, that y1 t star is less than y2 t star and y1 t is less than equal to y2 t. Okay, so this condition is what telling you that suppose this is y1 okay, then the y2 function will be less than, so t star will, there will exist some t star where they are different, and I'm taking the smallest one, I mean the first point where it is different, like that kind of thing, okay, or not the first one, but some I'm t star I can choose that, so that at this point they are not equal, so y2 is less than this y1 t star, and before that also either it can be equal or less than that, so its graph will lie below that, something like this, okay. The other case is like it can go like this, so like this. Yes. These two possibilities, this the second one is this one, and this is the first one, right? I hope this possibility is fine to everyone. So the such existence of t star I can guarantee, right? Is this fine? Okay, if this is fine, then I'll consider just in this domain. Okay, so you know that, so let us consider this case 1. So this is 1, this is 2. So I mean similarly you can handle the second case as well. So let us consider just the first one. So the first case says that y1t is greater than equal to y2t. So for all t belonging to t naught to t star. Okay, so t star. So this would mean, so since f is what? F is non increasing. So the sign, so f of t y1t is less than equal to f of t y2t. T star. Now this tells you, so look at this term. So this is what? fty1 minus fty2. So this tells you that z prime t is less than equal to 0. So for all t in t star. Now this will give you that z is decreasing, right? This says that zt is decreasing. On t star, and this would give you that z at t star is less than equal to z at t naught, and z at t naught, you know that this initial condition is 0, so this is 0, and this will give you z at, so z at t star is y1 t star minus y2 t star, so this is y1 t star minus y2 t star, this is greater than equal to, less than equal to 0, and from here you get y1 t star is less than equal to y2 t star, right? And this is a contradiction to this fact, right? So here we assume that y1 t star, the graph of y2 is always less than graph, I mean below the graph of y1, which is not true at t star, and this is a contradiction, right? So this is a contradiction to this assumption. Okay, this one. Is this fine? Okay. Okay, so this is just a sketch of the proof uh, for this corollary. Okay, so when f is non-increasing, you have this uniqueness of the solution. Okay. So now let us move to the Picard's theorem. Okay, so assumption is, the first assumption is same. Okay, so you have to consider a domain which is a neighborhood of t naught y naught. Okay, so this rectangle you consider. So the function f should be continuous in this rectangle. Okay, and the second condition is that it should be Lipschitz, that is it should satisfy this kind of condition. Lipschitz in y variable, not in the t variable. So for each t, and for y1 y2 in r, okay, so so this you can consider this ordered pair in this rectangle. So ft(y2) minus ft(y1) is less than equal to k times y2 minus y1. So this is called Lipschitz condition. So if f satisfies this condition, then again you define h in the same way, minimum of a and b by m. Then the initial value problem will have a unique solution on this interval. Okay, so and what is the extra assumption? This is the extra assumption. I mean, assumption on f. Okay, so if you compare to Peano's theorem, this is the extra assumption that what we are putting on the function f. Okay. Okay, so here also, like when we saw this theorem, we say that it will exist in some interval t0 minus h to t0 plus h. Okay, again the same h is also being said that it will exist on t0 minus h to t0 plus h. That means it is telling you that some interval the solution will exist and it will be unique. But the question is this h the actual, I mean, will this h give you the actual existence, I mean the actual interval of existence, right? So when I say y is a solution, I have some interval in my mind that y is a function from I to r, okay, and this is a solution, okay, I mean where this function is defined and it is differentiable and all those properties what we have for the solution. But the question is the I what we are getting from here, is this the maximum interval? Okay, the answer is no. So what this theorem is giving you, it is just saying you that in a neighborhood of t0 the solution will exist and it will be unique. Okay, it is not telling you that this interval what we are getting will be the maximum one. Okay, so the solution could exist outside this interval as well. Okay, so this is a limitation of Picard's theorem and Peano's theorem as well, that it is not giving you the maximum interval of existence. It is just giving you that, okay, in a small neighborhood of t0 the solution will exist. Okay, and we'll see this in the next example, that I mean an example where the maximum interval of existence is something else, while the Picard's theorem cannot give that maximum of interval of existence by any possibility of this m and b. We'll see that. Okay, so this is the example. Okay, so you have this IVP. Now try to solve this initial value problem, what you already know, like some theory of ODE. Okay, so you have y prime. Okay, let us first calculate the maximum interval what Peano's theorem gives us. Okay, so what Peano's theorem tells you, so here what is f? F of t comma y is given by y cube. So it is constant with respect to time. Okay, so it does not involve time. So it is clear that this function is continuous. So this is continuous on r cross r, right? It is continuous everywhere, but it is not Lipschitz, it is locally Lipschitz, right? So what I mean by locally Lipschitz is, so in a neighborhood of y, so suppose that this kind of situation what you have seen here, this k will now depend on, so here its k is not depending on the domain, but now this k, if this k depends on the domain what we are considering, so this y1 y2 is some particular choice, right? So it should belong to this kind of rectangle. Okay, and this rectangle has a length b, so I mean if this is y0, this is y0 minus b, this is y0 plus b. So depending on this b, this k is, if k depends on this b, then we say that this is locally Lipschitz. And if k is independent, so for example, if you take this function f of y equal to y, then we know that if you take f of y1 minus f of y2, this is equal to y1 minus y2, right? So this k is 1. So this is not depending on the domain. But here, this function, if you take this, if you want this kind of estimate, so the k what you will get here will depend on the size of domain you are considering. Okay. So that is what Lipschitz, locally Lipschitz means. Okay. So you can prove that. So how you prove that? So here you see this f function. So for example, let me g of y equal to y cube. You know that this is differentiable and the derivative is also continuous. So you can use some kind of this mean value theorem. So something like this, right? So g of y1 minus g of y2. This is equal to some g prime of psi lying between y1 and y2 mod y1 minus y2. Right? This is from mean value theorem. If you can bound this, then you are done. So here in particular, this g prime y is 3y square. So now the bound of this will depend on the size of the domain. Okay, so that is why this is this is one way of saying that this is a locally Lipschitz, that if a function is c1, okay, then we can say that it is a locally Lipschitz function. Okay, so here this f is locally Lipschitz, and that is enough for us, at least, because we are working in a rectangle. So that rectangle is a domain, and in that domain it is a Lipschitz function. Okay. Okay, so here let us consider the rectangle R. So what was R? R was collection of t comma y belonging to R2, such that, now see over here, this Lipschitz thing will not depend on time, right? So we can take t to be in R because this function is continuous on whole of R. Okay, but for the, when we are considering the rectangle, this y I will have to take in a some closed domain. Okay, so y should be y minus y naught. Okay, so here y naught is 2. Should I put it here, or okay, I think I should put, so y minus 2 should be less than equal to 2, some b. Okay, okay, so here a is infinity at this point, because f is continuous everywhere, so we can consider the whole domain of t. But for y we have to restrict, and the reason for restriction is that this function is not globally Lipschitz, it's locally Lipschitz. Okay, so in this domain, so whatever b we choose, so we'll have to make sure what b will have to choose. So we'll give some condition, we'll try to find the value of b, the optimal value of b, where we can achieve the maximum interval of existence. Okay, so you remember this h. Okay, so let me go one by one. So now this rectangle we will be considering where b is unknown. So here b is just unknown. So b is some real number, b is greater than 0 and is unknown so far. Any b would work. So any compact domain we can work it out. So now in this domain R, so here f is continuous in t and R, continuous in both the variable t and y, and it is Lipschitz. F is Lipschitz in y. Okay, so we have these two properties here. So this from Picard's theorem, this IVP will have, IVP admits a unique solution in the interval in I t naught, which is the t naught minus h to t naught. So t naught over here is 0. So in minus h, so let me write 0 here, minus h to h, right? And where h is given by, where h is equal to, if you recall, this is infimum of a, where and b by m. But what is a here? A is infinity, right? So what was a? A was the domain t minus t naught less than a. But a is now infinity. I am considering, so here t naught is 0. So just mod t less than equal to a. And we know that over here we are considering the whole real line corresponding to t. So that's why a is infinity. So infimum, so this will not contribute to the infimum. So what we are left out is b by m. Okay, and what was m? M was the supremum of or maximum value of this function f, right? So here this h, so what we want to do, we want to find the maximum interval where the solution exists. Okay, so we want to find the whole interval where the solution will exist. So by Picard's theorem, we are getting h as this one, b by m, where b is not known to us and m is also, m will depend on the b, the domain. Okay, so let us calculate what m will be. Okay. Okay, so recall, so let me write this rectangle. So in this case, this was your y, this was your t, t is the whole real line, this is y. In our case, we are considering the domain, so 0 and y0 was 2, so this kind of point 0 comma 2. Okay, so the domain what we are considering is some strip of this sort. So t is in the whole real line, but this is y0 or 2 minus b, y0 minus b, y0 plus b, and this is y0 equal to 2. So we are in this domain. Okay, so this is the rectangle R. Now let us try to see what will be the maximum value of f. So f of ty is given by this y cube. Okay, now m is equal to the supremum, what we can, so see, you want to maximize this quantity, that is your goal. Just keep in mind that we want to maximize this h, and that maximization can be done by some good choice of b. Okay, so that is my goal. So goal is to maximize h, which is given by b by m. Okay, so what is the maximum value? The m, the value of m, I will have to figure it out, right? So m is just the supremum over r of the function f t comma y. So you see this y cube in this interval will take the maximum value at the end point. So y cube is an increasing function, right? It's like this, it's increasing function. So the maximum will be attained at the boundary point. So this y at this point, so when y is in this line, the maximum will be attained. So the maximum value is 1 plus b, sorry, this is 2 plus b, y0 plus b, so 2 plus b whole cube, right? This is the value of m. So again, h is, now h I can write it as b by m, which is b by 2 plus b whole cube, right? Now our goal is to choose such a b so that this h is maximum, right? So our goal is to maximize this h value, right? So let us consider this function. I mean, so our goal is again to find b greater than 0 such that h is maximum. So such that this, the function b by h equals to b by 2 plus b cube is maximum. So now h, you can see as h is a function of b, right? So the moment you change b, the value of h will change. Okay, okay, so now let us try to see this. So consider the function g. Define this function g as x by 2 plus x whole cube. Okay, and now you differentiate it. G prime x, if you do, you take x outside, so you'll have minus 3 by 2 plus x raised to the power 4, and then so this is done, plus 1 by, so this is 1 by 2 plus x whole cube. And if you take 2 plus x whole cube minus 3x plus 2 plus x, this is minus 2x plus 2. Okay, so you got that so I want to maximize this function, right? So we have considered this function gx. I am taking the derivative. This is equal to this. Now if I make it equal to 0, so g prime, so for the critical point, so g prime x equal to 0 implies that x should be 1, right? So let us see how the graph of g prime will look like. So okay, so this is, let's say, the value 1. Okay, so at here g prime is equal to 0. So here g prime is equal to 0. Okay, so when you go away from 1, so if you take value larger than 1, then g prime is negative, right? And if you take less than, then g prime is positive. So this one point is the place where the maximum value of the function is attained, right? So g of x is less than equal to g of 1 for all x, right? This function is attaining the maximum value at 1. So here I will have to put b equal to 1. So let me write in. So gx attains maximum value at x equal to 1. Okay, and this is why, and thus the maximum value of h can be h is equal to, so I'll put b equal to 1 here, where it is here, so 1 by 2 plus 1 whole cube, which is 1 by 27, right? So let me conclude this whole discussion by, so Picard's theorem says that theorem tells that the given IVP has a unique solution y, has a unique solution yt for t belonging to minus h, that is minus 1 by 27 to 1 by 27, correct? So this is what we can conclude here. So was this calculation fine to everyone? Do you have any doubts?
Excuse me.
Yeah.
Not a doubt, but small maybe comment. Like we can even show this using Peano's theorem also, right? Because f of t comma y is not increasing. Y cube is.
Yeah.
So again, we can say that the solution is unique using the Peano's theorem as well.
There I think we say that it is non-decreasing, right? Or non-increasing. It should be decreasing. Here it's increasing.
Oh, okay.
Anyway, the goal here is not the discussion whether the solution is unique or not. Okay, so we have guaranteed by Picard's theorem that okay, we have a unique solution. But my main intention of considering this problem is that the value of h what you can obtain from Picard's theorem will not give you the maximum interval of existence. It will just say that in a neighborhood of t naught the solution exists and it's unique, but that will not be the maximum interval. Okay, so let us try to solve this. So what we have seen so far, that it has a unique solution in this interval. If you use the hypothesis of Peano's theorem also, you'll get the same value of h, because the h was defined in a similar manner in both of the theorems, right? So you'll get the same interval, but the question is this the maximum interval? So for that, let us try to solve this problem. The way we solve. Okay, just the usual calculation what we do. So let us consider this. So y prime, so let me use another color. So y prime is equal to y cube, and y at 0 was given to be 2, right? So again we can use the separation of variables. So dy by dt is equal to y cube. Okay, so dy by y cube is dt. So here again you can assume y is non-zero. Okay, and then if you just integrate, what you get is uh, what will be my y minus 2 by minus 2 equals t plus c. From here you will get yt. Okay, just let me write. So from here you get 1 by y squared t is equal to minus 2 t plus c. Okay, so y square of t is equal to 1 by minus 2 t plus c, right? Okay, so we have got the expression for y square. Now we'll substitute. So we were given that y0 is equal to 2. So from here we got y square of 0 will be 4. So substitute in this one. So if I substitute there, what I get is 4 is equal to minus 1 by 2 t plus c, and from here I get t plus c. Oh sorry, t is 0, so just 2c. So from here I got c is equal to minus 1 by 8. So the solution I can write it as y square of t is equal to 1 by minus 2 t minus 1 by 8, which can be rewritten as, so if I take 1, so I can take LCM, so it will be minus 1 by 4. So let me compute minus 2, 8t minus 1, and 8 will be gone above. So I have 4 by 1 minus 8t. Right, so this is how y square looks. I hope everything is correct. Is this fine? Is this okay?
Yeah.
So from here you see this y square. I mean, if y, we can verify, like we have used the OD to get till here. So from here we'll get yt, I mean square root of this plus minus of whatever we have. But here you see, to make, we know that y square is non-negative, so this would imply this is non-negative, and this give you some restriction on t. So t will be, so 1 minus 8t. So let me use some other color. This is greater than equal to 0, so from here I'll get 1 minus 8t greater than equal to 0, and this will give you t less than equal to 1 by 8. Okay, so when t, so let me write here, so for t belonging to minus infinity to 1 by 8, this y square makes sense, right? This function y square is sensible. Okay, so let me write for t, I am defining. Okay, so first let me find the solution to be more precise. So from here, okay, so let me, from here what you can say that y of t is equal to 2 by root 1 minus 8t with plus minus sign. One minus 8t plus minus, but you see the initial condition tells you that you cannot take minus, because if you put t equal to 0 you will get plus minus 2, but you have this initial condition, so you will just have to consider the plus sign. Okay, so this is yt. Okay, so for t in this, yt is equal to 2 by root 1 minus 8t. Okay, yt given by this is a solution for the given IVP, right? So you see this function is defined in the whole, this interval before 1 by 8 it is defined, and this will satisfy the differential equation as well, right? So this is the actual solution, okay, where the domain of existence of the solution is minus 1 infinity to 1 by 8. But from the Picard's theorem, so let me see, this was the t naught equal to 0. The Picard theorem told you that you will get 1 by 27 minus 1 by 27. Here the solution exists. This is by Picard's theorem. But when you actually solved it, you got that, so 1 by 8 will be somewhere here, let's say. So you got that this in this whole interval solution exists, right? So this is a limitation of Picard's theorem, that Picard's theorem will give you existence uniqueness, but in a small neighborhood of the t naught point. It will not be the actual one. Yeah, this is what I was meaning to tell you. With this problem, is this fine? Okay, so is this fine? Okay, so okay, so this I already discussed a bit when I told you about the Piano's theorem, but again you can verify the Picard's theorem as well. So in this case I already mentioned that this function f of t comma y, which was given by 3 by ty minus 3 by t. Okay, so this function is continuous in 0 infinity cross r, and it is Lipschitz in y over r. The y can belong to the whole domain r, because you see this is a linear function, so Lipschitz in y. So by Picard's theorem, so you can conclude that this has a unique solution. So by Picard's theorem, IVP B has a unique solution. Okay, so what I mentioned before, that yt equal to 1, which was the constant solution. So I told you earlier that yt equal to 1 for all t belonging to, or all t greater than 0, is a solution of B. Okay, but this Picard's theorem tells me that this is a unique solution, but okay, but this tells me that it is a unique in a small neighborhood of 0, but you can clearly see that this will be the unique solution in the whole 0 infinity. Okay, so by Picard's theorem we know that this is the solution. It's not just a solution, but is the solution. Okay, so it's unique. Okay, so let us move to the next problem. So you have seen the proof of this Picard's theorem, right? So where we define iteration. Okay, and you prove, so you define iteration of this sort. So Picard's iteration is given by y n plus 1 of t is equal to y0 plus 0 to t f of t comma yn, okay, s comma ds, right? This is how you define the Picard's iteration. So this is for n greater than equal to 1, no, n greater than equal to 0. Okay, so you have this kind of iteration, and then you show that this converges to some function y, and then that function y becomes a solution of this IVP. Okay, so this is how. So in this problem we have to compute this yn plus 1 for n equal to 3, sorry, n equal to 2. So you have to, so the question is that you have to obtain y3. Okay. So let us try to see how it looks. So let me try y prime equal to y, and y0 is 1. So this is the IVP in the consideration that we have. Okay, so we know that y0 is just this constant function 1. Okay, so this is the first approximation that we do. And now you calculate y1 of t. So y1 of t will be given by y0 plus 0 to t f of s comma y0 of s ds, right? And this is y0 is 1, so this is 1 plus 0 to t. And what is the function f? So here you note that the function f t comma y is y. So here f of s comma y naught s is y naught of s, right? And y naught of s is what? Y naught of s is 1. So this is 1 times ds. Okay, so you get 1 plus t. Okay, now let us try to see what is y2. y2 of t is again y0 plus 0 to t f of s comma y1 s ds. Okay, so this y0 is what? 1 plus 0 to t f of s comma y1 s is y1s, and y1 s is 1 plus s. So this is 1 plus s d of s, which is 1 plus s square by 2. Okay, now let us calculate y3. So y3 of t is again y0, which is 1 plus 0 to t f of s comma y2s, which is equal to y2s. And what is y2s? Okay, so here it will be t, sorry. So when you integrate, you will get t. Okay, so now if you put f of s comma y2s, which is y2s ds, and y2s is this function, so this is 1 plus s square by 2 ds, and this is given by, if you integrate, you will get 1 plus t square by 2 plus t cube by 2 into 3. Okay, so let me rewrite it as 1 plus t square. So 2 is just 2 factorial, t cube is by 3 factorial. Okay, exactly. So we are converging to that. It's not like that. I mean, I cannot say this will converge to what you are saying. It will converge to the exponential function. And why is that? Okay, so see, so okay, so far we have proved that what is y3, and if you try to go on in this way, what you will get y and t, as he already mentioned, that it is Taylor series expansion. So if we calculate yn of t, it will be 1 plus t plus, like that it will go till tn by factorial n. Okay, and why it is happening? So you know that this yn eventually converges to the solution y. Okay, so what we do, so when we get this, when we saw that yn converges, we saw that if we take the limit, then we get yt equal to y naught plus 0 to t f of s ys ds. Right, so under the assumption, so if limit n going to infinity yn is y, then we get this, right? Then we have this, and then we say that this y is the solution. So this limit of this iteration is converging to the solution. Right, so in this case, you see what is the solution here. So for this equation, you know, if you solve this, this is again dy by y equal to dt, and if you solve it, we'll do ln of mod y equal to t plus c. So this would give you yt equal to e raised to power, so some constant c times e raised to power t. Now if you use this initial condition, you will get yt is this, because when you put t equal to 0, you'll get c equal to 1, so you'll get this. So this is the solution what we have, right? And this iteration confirms me that okay, that this will be the solution. I mean, so this iteration you can clearly see that it converges to the exponential function, which is the solution of this IVP. Right? So this is the why we are converging to exponential, because of this fact. This solution is given by exponential. Okay, so now let us proceed to this problem. Okay, so we'll try to solve this equation. Okay, so let us first try to see what is the fty. So let me write in this page. So f t comma y is y raised to the power 2 by 5. Okay, and t naught equal to y, t naught y naught is given by 0 comma 0. Okay. So we'll have to consider a neighborhood of this, right? So you can clearly see this function y is a continuous function. Okay, so this is a continuous function on r cross r, right? So with respect to t also it's continuous, and with respect to y also it's continuous everywhere. But you can check that this is not Lipschitz, because the derivative, if you do, it is unbounded near y equal to 0. Okay, so that is a reason you can check that this is a not Lipschitz, okay, with respect to y. Okay, I mean y around 0, because this is the point we are taking into the consideration. So let me write somewhere with respect to y in any neighborhood of y not equal to 0. Okay, so it's not Lipschitz. So from here, the Peano's theorem guarantees tells us that solution exists. Okay, that's it. That's all we can say. We cannot say the uniqueness. Also, you cannot use that corollary as well. Okay. Okay, so we can guarantee that the solution exists, because this is just one. So I mean here Picard's theorem is not applicable. Hypothesis of Picard's theorem is not satisfied. So if it's not satisfied, we cannot say that it will not have unique solution. We can just say we don't know. That's all. Okay, it is not giving the necessary condition. So the hypothesis is just a sufficient condition to guarantee the uniqueness of solution. Okay. Okay, so let us try to solve this problem explicitly. So y prime is this f, which is y 2 by 5. Again I'll use the same thing, dy y raised to the power 2 by 5 equals to dt. Okay, so y is not again equal to 0. Okay, so I mean, so one thing let me tell you. You see, this for this IVP, y constantly equal to 0 is a solution, right? So y equal to 0 is a solution. Okay, now we'll assume that y is not 0, and then we'll try to see. So when we have to solve this problem, we can use the this method of separation. Okay, so this dy by dt is equal to y raised to the power 2 by 5. So this I can write as dy by y raised to the power 2 by 5 dt if y is not 0. Okay. Now again, if you integrate, what you get is y minus 2 by 5 plus 1 by, so this will give you 3 by 5 equals to t plus c. So from here you get y 3 by 5 is equal to 3 by 5 t plus c. Okay. Now if I use this initial condition, y at 0 is 0. Okay, so I mean, so see, this is just a method, okay, to solve the problem. So I am saying that if I have the expression of y in this way, then this will solve the differential equation. Okay, so let me write separately. So I'm just writing this as a conclusion. So yt, okay, so yt equal to, so this 3 by 5 t plus c whole raised to the power 5 by 3 solves the differential equation. You can check this. Okay, so if you differentiate it, you will get this. Okay, so this solves the differential equation. So I mean, this is the first doubt session, okay, for this course, and obviously this will be uploaded, so you don't have to worry, you will get the video as well as this slide. Okay. Okay, so this solves the differential equation. Now to solve the IVP, let us put the initial condition. So the initial condition, what? Y at 0 is 0. So t equal to, so y 0 equal to 0 implies, so if I put t equal to 0, I'll get 3 by 5 c 5 by 3 equal to 0, and this will give me c is equal to 0. Okay, so yt equal to 3 by 5 t raised to the power 5 by 3. Okay, so again 3 by 5 raised to the power 5 by 3 is another solution of the IVP. Okay, so we have got two solutions. So can you construct so do you know this thing? I mean, if you have two solutions for a homogeneous kind of equation, then you can construct infinitely many solutions. Do you know this? Yeah? Do you know this fact? Okay, so let me tell you. So I'll just tell you just graphically. Okay, so see what we have got so far. So this was the first solution. So this yt equal to 0. So y identically equal to 0 is one of the solution. The second solution what we obtained is this one. So see, this is t raised to the power some 3. So this is t 5 by 3, which is equal to t 1.66, like this. Okay, so it's like this kind of thing. If you plot it, it's a polynomial, so you'll get something like this. Okay, so for t negative, it won't be defined. Okay, so I don't actually know the graph. So what could be the graph? So t 1.66, so it's like if you take negative power, I don't know, whatever the graph be. So for positive, I can say that it's like this. right? I mean something like this. And for negative, I'm not sure how this will look. It will be 1.5. It's like, I don't know. So let us just consider t greater than 0, okay, for simplicity. So do I have any restrictions? So okay, so for t, so let me not draw the graph, so it's better not to draw. Okay, so let's be more, so we know, so let me rub this also. I will not tell anything about the graph, but it's like yt equal to 0 is one solution. Okay, the second solution is this given by this, so y1t, y2t, or let me write another notation. So it's y0, I don't want to use this kind of notation, so yt, let's say, and then y tilde t, you define it as this function 3 by 5, so sum c 5 by 3 t power 5 by 3 is another solution. Now what you can do is, so see till t, so I mean you can define it in this fashion as well. So so you do one thing, so suppose till, so suppose this is the 0 point, you know that the function y should at 0 it should be 0. Okay, this is you know by the initial condition. Now what you do, till here you take y equal to 0 solution, okay, this one, and now you use this solution, the another one. Okay, you can check that this combination will be differentiable and all. Okay, so because the derivative if you do at t equal to 0, you will get 0, which is the case of this one. So this is a c1 function. So till 0 you take this function, and after 0 you take this function. That is another solution. Now this can be done in a more general thing. So you choose any alpha. Okay, so choose some alpha greater than 0. Okay, so this is a greater than 0 function. If you choose till here, what you do, you take t equal to 0 till here, and now you use this type of function. Okay, so now for any alpha positive, you can make it shift, you can shift it. So in most general thing, what I can say is y alpha t will be, so why I have to shift it just in the forward direction, because if I cannot shift it backward, right? So I cannot do like this, because at t equal to 0 I have to take, the function should take the value 0, so I cannot shift in the left, but I can shift to the right. Okay, so you can define for alpha positive, so for, okay, so alpha is greater than 0, so y alpha t will be 0 if t is less than equal to alpha, and after that you will take 3 by 5 this constant t, you're shifting it, right? So it will be t minus alpha 5 by 3 if t is greater than or equal to alpha. Okay, where alpha is greater than 0, you can check that this is a differentiable function and it will satisfy the differential equation. So here this is for all alpha greater than 0, so you have infinitely many solution. Okay, so the IVP has infinitely many solution. Okay, is this clear what I have done? Okay, if it's clear, then let us move to the next question. Okay, so this is quite, any doubt? Okay. So this question is like, if suppose you have a function x, okay, defined on interval -1 to 1 to r, and it's a continuous function which satisfies this identity, okay, that xt is equal to x0 plus 0 to t xs. Now you have to prove that x square t will satisfy this identity. Okay, so can you tell me, do you have any guesses how you can solve this? Clearly, if you take square, then it won't give you this identity. If you take the square, you will get a plus b whole square, and then you won't get this kind of thing, right? Do you see this?
I mean, this is the, like, since x is a continuous function, this x of t is equal to that first equation, we can write it as dx by dt is equal to x.
Correct. Okay, so what he's suggesting, obviously this is a differential equation course, so obviously I'll be talking about the differential equation. So by the fundamental theorem of calculation, as he's saying that we can differentiate this identity. So by using fundamental theorem of calculus, we have x prime t equal to x of t. Correct. Now what we can do? So you have reached till here.
And maybe one way which I could think of is solve that equation, substitute back here and verify whether this is true.
Okay, so let us do that if you want. So what will be that? We'll get xt equal to e raised to power t, right? Am I right? Correct?
Yes.
So now let us take the LHS thing. LHS is x squared t, which is e raised to the power 2t, and RHS is x0, which is 1, 0 to t, and then you have, sorry, it's x square 0, right? And then you have 2 times x square s ds. What we have is, so x square 0, let's keep it like that, 2 0
This
to,
x of t,
so this will be e raised to power 2t, right? 2s.
x of t is like x of 0 into e to the power of t, right?
Where? You are saying here,
X
right? What are you saying? I didn't get.
Yes.
I'm
You
just
wrote-
trying to solve it, that's it. What you are saying is
while
correct.
solving that, you assumed x of 0 is equal to 1.
Yeah, so this is 1. This is what you are saying? Yeah,
Yes,
this
yes,
is 1.
yes. Right to say
This is
that.
1, 2, and if you integrate it, you will get e raised to the power 2t minus 1, right? And then in denominator it will
E
be
power
2.
2t by 2.
Correct. So you will get e raised to the power 2t, which is equal to the LHS, right? So you got that, okay? By solving this differential equation, we can prove this identity. Okay? Is this clear to everyone? So this is one way of doing it. What you can do, you can just use this differential equation itself, and then you can get that identity directly. Okay, so this is one way where you solve this equation. Okay, so this was one way. The second way would be, what you do?
Multiply x on both sides and
Exactly, yeah, you are right. So if we can multiply by x both the side, what we get is x prime t xt equal to x square t, and then this is nothing but d dt of x square t by 2. This is equal to x square t. Now you integrate with respect to t from 0 to tau, so you will get x square tau by 2 minus x square 0 by 2 is equal to 0 to tau x square t dt, and then you got x square tau equal to x square 0 plus 2 times 0 to tau x square t dt. Okay, and this is what you were required to prove. So either you solve it explicitly or this way. Okay, so do you have any doubt? So this was the last problem for today. If you have some doubts, you can ask. Okay, if there is no doubt, do you have any suggestion to make regarding the tutorial sessions or this live session?